We previously used symmetry to talk about molecular motion and vibrations, but here we'll talk about using it to apply symmetry to the idea of forming linear combinations of atomic orbitals or wave functions, because orbitals are also wave functions. And we'll use these to then think about how they interact. So orbital overlap is critical to understanding how bonding works. So the more covalent bonds are when they have orbital overlap, which is reliant upon symmetry. So if you have atomic orbitals of the same symmetry, then they can form bonds because they can then interact through overlap. Who knows what I'm saying right now? It doesn't matter. Okay, so here is my list of rules for how to see how atomic orbitals overlap. So the first thing we want to do is, if you have your molecule, you want to assign the point group of the molecule. So hopefully you're already a master of doing that. So you're very good at that. So once we have a point group assignment, then we can figure out how, which your basis set is. So what atomic orbitals are the ones that are interacting. So what I'm writing here is identify basis set atomic orbitals. So the most important atomic orbitals in your molecule are going to be the valence orbitals of each of your atoms. And this is because the valence orbitals are the highest energy ones and the biggest ones, so they're the ones that overlap. If you think about a sulfur atom, which has 1s, 2s, 2p, 3s, 3p orbitals, if you think about the 1s orbitals of them, they're very contracted. Let me time it when I shrink in. Oh, I guess I didn't. Yes, 1s. I'm sucked in right now. And then so the 3p orbitals and 3s orbitals are out there. They're more diffuse, and then they're the ones that overlap when you form bonding. So that's why it's very important to figure out what the valence orbitals are. Not that the lower orbitals can interact, but they just interact less. So again, we're talking about bonding. Once we have our basis set, then we need to figure out, the third step is to figure out the symmetry of your basis set. So here is where understanding character tables comes in. So find symmetry. So there's two aspects of it. If you have a central atom in your molecule that's sitting on like your axis of rotation, for example, then you can actually very easily identify how the atomic orbitals of that central atom transform in your point group. And what you can do is then just look at the right-hand side of your character table, and you can see how the functions transform, because you know how the linear functions, the square functions, et cetera, they all transform in space. So I'll just write an example here. If you have an s orbital, there's a circle. That's going to transform as x squared plus y squared plus z squared, so you can figure out what that says in the column, and then that's going to be your s orbital. Typically, that's the most symmetric representation, A1, A1G, etc. Your p orbitals transform as linear functions, the x, y, z functions. And so they're directional. And then lastly, your d orbitals transform as the square functions, xy, xz, x squared minus y squared, oh, yz. And what's the last one? Yz, or no, z squared, dz squared. So keep in mind, again, this is only for the central atom. If you have non-central atoms, you have to actually do a different operation to figure that out. So let's talk about non-central atoms whenever I get there. Oh yes, again, boxing central atom is the one that transforms as those functions. So for non-central atoms, we have to build up our linear combination of atomic orbitals using symmetry adapted linear combinations, just like we did for vibrations. So we want to find a gamma reducible. And then these are going to be for atomic orbitals within the molecule that are related by symmetry, and then we could then reduce it down to find the symmetry of these groups of atomic orbitals that can then form linear combinations. Okay, once we have how these transform in space, we can then decompose to a sum of irreducible representations. So those, then we can have the symmetry labels for these linear combinations, which will be an irrep. So just like we had irreps of vibrations, we'll have irreps of linear combinations of atomic orbitals. And again, these are the valence orbitals of our non-central atoms. And then lastly, we can then use projection operators to, once we have the irreps, to then figure out what the combination actually is. We have coefficients, we'll have phases, and then we can have these in symmetry in space. So don't worry, we'll do an example of this in the next video with, again, a crazy voiceover. Who knows what I'm saying right now? My hands are waving in space. Don't worry, we'll do examples in class. Goodbye.